Thank you, everyone. Thank you for joining this call. I see you guys have come and you're quite numerous, which is wonderful. Only puts more pressure on us, I suppose. So what's this presentation? What's this webinar going to be about? I presume you probably read the title, but it's going to be about precision maintenance practices. And what we will look at today is we will do an overview of precision maintenance practices. Overall, we're going to talk about many of the pillars of precision maintenance. And I'll show you that in the agenda. So who will be presenting? Well, there's two of us. It's going to be co-presented. It's going to be Dina and myself.
I'm relax, relax. ঠিক আছে? Bye. তুমি ওকে আমি চাচা বলতেছ?
Okay. Mute those, sorry. So there's going to be Dina and myself presenting mostly. Well, Dina's going to be presenting for the most part, and I'm just introducing this webinar. I'll come back towards the end to maybe answer some questions and give you some contact information if you so wish to do that. But Dina will be the primary presenter. So who are we? Michael. I've been working for Spartacus, which is now a division of Reliability Solutions. I've been working here for about 3 years, and before that for about 2 years, back when Spartacus belonged to Laurentide. So I've got about 5 years of working with the company as an SME. So I'm an expert when it concerns everything the Spartacus platform. And I will be the support. I'll be Dina's support. Dina, who are you?
Yes, Dina Brown. Good afternoon, everyone. I've been with Reliability Solutions for 21 years now as a service provider and now a training manager or one of the training managers there. Prior to that, I worked in the paper industry for right at 23 years. And there I was a millwright, and then I became a training coordinator or precision maintenance trainer before coming to Reliability Solutions.
Perfect, thank you. So just before we start the webinar, I want to give a bit of context who we are. Reliability Solutions. We offer four kinds of different services, or four kinds of services that you see listed in 4 different corners of the presentation. The reliability services, so site assessment, lubrication, asset strategy development, MRO, and so on. We've got the skills development, reliable organization, skill assessment, and there you'll also see precision maintenance. So what we will be doing today will be a specific focus on this portion of our expertise. But keep in mind that is really just a portion of our expertise. We also give field services, so on-site condition monitoring, planning, scheduling, and so on. And we have the last part here, which is not exactly a service, it's a product. It's the Spartacus APM software. It's a platform that essentially allows you to track your maintenance, execute your maintenance, and look at your asset or plant health so that you can better plan your corrective actions. So what will be on the agenda? So today we will talk briefly about what is precision maintenance, the philosophy of it, and then we will take probably 4 or 5 minutes for each of the, well, approximately five or so minutes for each of the core principles of precision maintenance. So we'll see vibration, assembly errors, documentation, precision measurement, and so on. Keep in mind that because this webinar is only 1 hour, well, 1 hour I suppose is a decent amount of time, but precision maintenance is a very large domain, okay? And we did have to cut out some of the domains such as pipe strain. We know they exist, but we decided that we had to focus, and these are the ones that we want to present to you today. If you have any questions today, please raise your hand up. You know where the your yellow hand raise up is, and we will do our best to answer the questions. That being said, we will be trying to follow a tight pacing for this presentation, and if we don't have time, we'll try to stay a bit longer at the end to answer your questions as best we can. And if we still can't answer your questions there, then we'll always be available. You can contact us by email and it will be more than happy to assist you. So from the next part on, I will let my colleague Dina present.
Okay. So what is precision maintenance and why does it matter? Well, precision maintenance is pretty simple and straightforward. It's about doing the right thing. It's a proven, improvement-based process. And note that I said process because you'll hear people say we do a precision maintenance program. It's not a program because a program has a beginning and an ending. It's a continuous improvement process. It takes a proactive approach to equipment, whether it's in the installation process, the maintaining of it, or operating of the machinery. And of course, this results in reducing failures, thereby reducing the cost, and of course, improving our reliability and our product quality. And many times we get a bonus, like a reduction in energy. So we can easily see why it matters. So when we talk about maintenance practices, how do we manage our risk? You know, maintenance management is very much like risk management. How do we control those failures? We have to choose the proper maintenance practice on our equipment. And of course, you will see here, run the failure, schedule, repair, or replace condition base of life extension. We have to choose the right one for our equipment because all of our equipment is different. It's based on criticality and other things about that equipment. Next. So we'll look at the schedule or repair for a moment. Of course, this is the B pattern from the Nallen and Heap patterns, and everybody's pretty much familiar with that. And of course, it says the older the equipment is, the more likely it is to fail. How many people agree on that? I mean, if that's the case, couldn't we just figure out when the failure occurs and then we could do what? Change it out before it fails. That would be ideal if this were true, wouldn't it? But we have to keep in mind when we look at this pattern, it only happens about 2% of the time in our equipment. Now, how equipment really fails, there's a total of 6 patterns that I'm sure most of you are very familiar with. And I want you to look at that A, B, and C column there. They're all random type failures. And then when you look at D, E, and F, next, wear-related, age-related failures on the first column, A, B, and C, and random failures over on D, E, and F. When we take a look at those random failures there, it says 89% versus failures that are based on wear and so forth, age-related, it's only 11%. So where's the bang for our buck? It's needling in on those random failures, and precision maintenance helps you do that. And of course, coming from the Nallen and Heath study, the failure development period, or P to F curve, was developed. Of course, that's just from when the potential failure is detected over to where we have a catastrophic failure. Keep it in mind that before the catastrophic failure, we can have what? A machine that's functionally failed for us. It's not doing what it's supposed to do, although it's still running. So keep that in mind. And within that FDP period, there's different tools we can use to detect things. Of course, you have your early detection, like your ultrasonics and vibration analysis, even oil analysis. But many times we can put simple tools in the hands of our technicians or mechanics or millwrights or whatever, and they can find issues out there as well, especially if you don't have a vibration analysis program or whatever is going on in your facilities. Of course, this is the area of influence from us, from look, listening, and feel using the human senses. But by that time, it's pretty much gotten very, very close to catastrophic failure. So temp guns, strobe lights, stethoscopes, whether it's a screwdriver or a wooden stick, little things like that help as well. Of course, maintenance philosophy, we just looked at this earlier. The big deal here is looking at run to failure, preventive, predictive, and precision, and why we should always be choosing precision. All of these practices have a place in our world, but if you look at the bottom 3, although they're very good with their intent and used where they should be, they're all failure-based versus the top one, precision, that is improvement-based. So no matter what practice we choose, we should always be doing precision, doing it right, even with run to failure, so it will last as long as it possibly can. Next. And of course, we took a little bit about vibration. Why vibration? Vibration is the leading tool to tell us the health and condition of our equipment to start with. And we know if it vibrates less, it's usually running smoother, it's going to last longer, and it's cost less to maintain. That's a win-win. And of course, what those numbers will be based on a lot of things like process criticality we spoke of earlier, machine speed, repair time, what's involved, how long does it take to get the parts, comparing machines across each other, similar machines. And of course, what's inside of that machine, what's the failing components in that machine. When we talk good or bad, there's some simple tools that we can put in the people on the floor, the technicians, the mechanics, the operators in some cases, that they can measure. And they want to measure usually 3 places, usually close to a bearing, all across that machine so it can tell them what's going on with that machine. And of course, I mentioned simple tools. Don't always tell us what the actual problem is the way our analyst could, but a simple meter or a vibration pin, you can have troubleshooting charts to tell you where you get highs and lows and so forth in certain places, what the issue may be. But the big thing is it tells the person on the floor when something is good or when something is bad or when that machine is just in a position that it needs attention somehow. And of course, assembly errors. If you look at this mechanical failure pie here, you will see that assembly errors, misalignment, and imbalance. That's a 30-30-30. That's 90% of the causes of our mechanical failures. If we jump on those, which is a big deal within precision maintenance, we can reduce a lot of failures. And of course, within the assembly errors, are we always torquing? And when we do we torque properly? Do we use the right sequence, the bolt pattern, and so forth? Pipe and or conduit strain. Do we check those things? Little things like key length. You know, most people don't think it matter, but all we're trying to do with our key formula that you'll see over to the side is to replace the mass that was removed and the position that we put these keys in, the positions we tighten our set screws down, pull threads, offset collars, how we set up those collars so that things won't wobble across and the shafts will run in the same plane with each other, grease quantities, and of course, positioning the grease in couplings and other component parts. Misalignment. Now, that's what everybody wants to jump on, but if we don't take care of the assembly errors beforehand, you're still going to have a problem machine. But everybody wants to pull out a laser or whatever and do an alignment, right? And it does great things for our equipment. But we have to take care of things like short leg, soft foot, angle soft foot. We have to torque the bolt so the machine will pull down consistently. Otherwise, it's going to give us different readings all the time. Of course, aligning our equipment restores that bearing clearance that we lose when it's misaligned. We have to take thermal growth into consideration. Machines change when they're up and get to their normal operating temperature. Other machines in the area might affect. Machines can get into frequency with each other and cause resonance and so forth. And always ask yourself, are the published tolerances good enough? And of course, we talk about case deflection and so forth, twist from pipe strain or soft foot or whatever in your machines, which is going to cost you life on those pieces of equipment. Yep. Unbalance, another one of those 30%. You know, we tend to suffer from what we call, or like to call, shiny metal syndrome. You know, we get a part in and it's all shiny and new. It looks round, it looks perfect, it looks like it's bored true on center. How do we know? Do we check for things? I mean, if you think about an impeller, most of our impellers are casting porosity. You know, are there any voids? Is there a denser area? Run out. Do we always check run out on shafts and other components to make sure they're round, that they're true, that we don't have any high spots? What are your machining tolerances? Are we always meeting those specs? Because that can change things across the machines. And of course, operation. Just the operation of the equipment sometimes can cause unbalance. You have different equipment that'll get build up on something that's rotating, like a fan or something, that'll throw it out of balance. Erosion, corrosion, anything that changes the mass can change the balance on that machine. And as you can see from the picture, we want our rotating equipment to rotate around a center. A heavy spot or so will throw that out. Those vector forces will throw it out every time, and it's going to beat up everything around it. There's other failures, resonance, like I spoke of. And of course, you can have bearing problems, whether it's a rolling element bearing or a plain journal bearing around motors and things like that. You can have problems with your rotor bars or air gap, gear mesh noise. causing early failure in your gearboxes and so forth, pump pulsations in your pumps, and of course, system overloading. Keep in mind, system overloading isn't always from the product that's going through that system. It can be some loads that we have left on that machine by not doing the right things on that equipment. And of course, documentation. We cannot stress documentation enough. We need to be able to track and trace and know the history on that equipment. It would be nice to be able to go back into the system and see who worked on it last, what kind of problems they had, and any special notes they might want to hand on to someone else. But it also helps us make a lot of determinations about that equipment. So there's software available for that. And if you have to write it on paper and transfer it or whatever, we need that information.
Out of curiosity to the people on the call, can you guys raise your hand if poor or lack of documentation you would say is a common problem at your plant? Yeah.
That's
Yep.
usually the case.
That's most of the people here on the call. So that gives you an idea. These aren't made up. We're not inventing these. We lack documentation. We have poor documentation. I see it all the time when I go to various plants, and that's even the documentation to do the work, or documentation on the machine. But after that, on the maintenance plan, we also have those things. So those are also things that are part of precision maintenance that we need to absolutely get a grasp of and better control of. Thank you, everyone.
And of course, precision measuring tools and fits and tolerances, so important around our equipment. So we need to have the tools in the technicians or the mechanics' hands and so forth when we're talking about working on equipment, so they can check things. They can make sure that that shaft is correct for that bearing, or that housing is not out of round or whatever, because all of those things can cost us life. They need that micrometer. They need those dial indicators to check run out and so forth. They need those inside mics or snap gauges to check for roundness and so forth on bores and openings and all. So we need all, and this is just a start there. We need all of those tools. So what happens when we have improper fits, and how does it manifest themselves? How about system rubbing? I mean, most of us have put together a rotating piece of assembly, and then we turn it and we feel a little rub. Did we set everything right? Did we check all our tolerances and clearances and so forth? That's huge. Or mechanical looseness. When it doesn't fit the way it should, then your analyst is going to pick up on looseness in that machine right away, and we're going to have a premature failure. Fretting and fatigue. When something doesn't fit quite right, you get minute movement between those two surfaces, like between the surface of the shaft and the inner ring of a bearing, and it frets. The bent and worn components, of course, speaks for itself. Then you have Bernelling. You have true Bernelling and false Bernelling. True Bernelling from impact damage, and false Bernelling from oscillation of vibratory action acting on a machine when it's down. And we see that a lot in bearings because people aren't rotating spares and so forth. Of course, misalignment and unbalance speak for themselves. And of course, overheating, leakage, slowing down the machinery. And of course, we end up losing the function of that equipment. And those last three apply across the board, but especially around hydraulic systems. But keep in mind those fits and so forth, the way we put things together really governs the performance of that piece of equipment, not to mention the life of that equipment. And of course, this is just a standard ISO fit chart where you'll have those letters and so forth and know what they mean, know what type of fit you need. If you have a uppercase or capitalized letter, you know it's referring to the housing. And if you have a lowercase letter, it's referring to a shaft. And usually, and there's a number that follows it, not shown here. But when you look at the charts, you make sure that you look at the right column for the type of fit you need for your equipment. Make sure it's within that shaft, is within that range of whatever it has to go into. And of course, soft foot. A lot of people don't think it matters. Usually when it's just plain soft foot, we refer to it as short leg. And then there's angular as well. But soft foot is a big deal across our machines because and it's just a short leg like you see here in the picture, just a gap between the bottom plane of the foot and the top of that base in most cases. And of course, if we don't go in and feel that in a very controlled manner, what happens? We'll tighten or torque that foot down and it distorts or twists that casing housing the frame. And that affects all the internal components. And that last picture, the third picture over to your right, when you take a look at that shaft center line, and it's all about shaft and center line and holding that position, right? Every time you tighten and loosen that machine, or that foot that has that soft foot, it changes that position. So it gives you inconsistent readings on the laser. It never stays where you want it. It's put in 10, take out 9, move to the right, move to the left. You're back and forth. And we've all had a machine to dance at some point. A lot of times it's soft foot. And of course, that twist and distortion that it causes in that housing by twisting that machine can take your bearings out around, take the clearance out of them. It can cause internal misalignment. I mean, if you look at that little small machine out to the side, that internal misalignment is saying it's trying to deflect that shaft center line by like 1/8 thou. Little small machine like that, the bearing there at that front end, that inboard side, doesn't even have that much clearance in it. So it's going to lay its life down right away. The deflection out on the end of that shaft, saying like 16,000 due to a soft foot, your laser doesn't know that. Or your dials don't even know that. Some things we have to do physically. So we need to check those things because it's going to try to align it out there. It's not misalignment. It is due to a soft foot. And of course, this is just a great picture of short leg, just a gap between the bottom plane of the foot and the top of the base. And of course, just a couple of samples of angular foot, different kind of animal, but it still needs to be fixed because it can still distort and twist that machine. But we fix it a little differently. We go over that very, very closely in the classroom. Just a sampling of some of the documentation we would use because you want to go all the way around and check everything and start with the worst foot first and double check the others before you try to jam something under there because fixing one foot can affect another foot. So do keep that in mind.
So I've got another one for the people that if you can raise your hands. How many of you guys actually do in-house the soft foot, short leg, proper and angular foot inspection on a regular basis, like it's part of your installation plan? You guys do that? Yeah? Few?
Yes.
Some. So I see it's about, okay, maybe like 60%. So it's good. It's good. So that it's being done. And that's for the 60% of you that do do it. And for the others, well, it's an opportunity to catch up. And yeah, I see you talked about laser alignment. They are related, I suppose, but they are essentially two different problems to handle with their own respective solutions. Thank you, everyone. You can bring your hand back down, unless you have a question. Oh, I see a couple of people bringing down their hand. I'll check. Dennis Morris, you have a question? Oh. Okay, Sean, looks like you just raised your hand, so I'm guessing you have one.
Actually, I didn't. I might have thought I had it up, but I was just going to say in regards to the dialing, it's part of our dialing process, but I don't know that it's always completed properly. So we're still working on it.
Great. Well, good for you to at least have that part of your plan and your program. And doing it properly would be then the next step to ensure that it's done properly and systematically is definitely something you'd want to look at from your perspective. Okay, thank you. I'll continue.
Fasteners and torquing, very important to our equipment. The way we tighten and torque things down can make all the difference, whether something will leak or whether it will stay in that position, whether that bolt is tight enough, whether we get twist or distortion in our systems. It can make a difference. Of course, talk about loose, you check by hand. Keep in mind it could still be loose and you can't move it with your hand. It may not be where it needs to be. Stud length can cost you because if it's too long and you're threading into something, it will bottom out and you think you got it, but you don't have it. Too short. If you're going through a nut on the other side, of course, you should have a couple of those threads on the outside so you get the full strength of that fastener. And of course, over tightening and leaving things too loose is a problem. Over tightening, of course, can cause you to have cup washers, especially if you're not using the correct hardened type washers and so forth, and pull threads depending on what you're threading into. So we should be very, very familiar with bolt grades and the materials we're threading into and so forth. And of course, corrosion, as you can see in those pictures, that affect our torque on our bolts as well. And of course, looseness, you'll get fatigue in the bolt. It will break for no reason over time, over cycles of movement in it because it's loose and we don't even realize it. Mechanical properties of a bolt. We need to understand tensile strength and proof load and the yield point of a bolt, the importance of torquing correctly and adjusting that torque if we're using some type of extension or some type of lubricant. But we want to stay in the proof load area, the elastic range. You do not want to get into the plastic range. Once you're in the plastic range, it is permanently deformed. It will still pull and hold a little bit, but when you get to the end of that plastic range, not only if that is deformed and won't ever come back, but then it's going to start to pull apart. And most people has felt that. If you've been out in the field long enough, you have felt that bolt start to pull apart, especially smaller bolts.
Yeah. And it's really important to look at this slide and to understand, in this example, we have a bolt, but this really applies to all metallic systems, right? They all suffer from this, and they're often not properly considered so that they be used only in their elastic range, unless specifically designed
Absolutely.
to be used otherwise.
Rough to precision. When we talk about alignment, of course, we're going to rough in, right? We rough in just to get our indicators so they won't be so crazy when we do a rotation or get our lasers within range. So rough to precision. And of course, understanding alignment. Keep in mind, when we talk about alignment, it's all about that center line position. And when we rough in, we're only doing what? Putting a straight edge across a coupling or a shaft or whatever. That's not always true and close enough. And of course, that's eyeballing. That's still eyeballing because you're eyeballing the straight edge. So keep that in mind. We want some type of tool to get us center line to center line position all the way across the machine. Of course, we have two types of misalignment. You have parallel offset, which is higher or lower, or one way to the side or the other, if you're talking about horizontal. And then we have angular. We have angular. And of course, with angular, if you are still roughing in, you could use a rise over run and do some calculations. And it's pretty simple. You can measure the gap from one side to the other or the top or the bottom of a coupling and get that gap difference and divide it by whatever your sweep is, which would be your coupling diameter. Measure from the center of that coupling to a foot, and it will tell you what to put there or take out of there if you're talking about vertical, or how much move side to side if you're talking about horizontal. So it's a simple formula there. It works the same way as what you're seeing here in the picture, the step risers. It's just rise. How much does it rise over a certain distance? Like the pitch on the roof of your house as well. Now, in the classroom, we use, and we can demonstrate lasers and so forth for people a lot of times, but we use reverse dial. And this is just showing you a reverse dial setup. It's set up very, very similar to a laser. And we're talking about measured points. And you remember I talked about the center line. You'll see across this machine, you'll see what we call a cold alignment line. That's our shaft center line. And we want that to be like one straight line across that machine, depending on what the tolerances are. If it's above 2000 RPM, it's 1 thou at every measured point, and every line you see there, the black lines, the blue line, the red line, they're all measured points. And we want that machine to be within that 1 thou if it's above 2000 RPM, within 2 thou if it's 2000 RPM or below. But that's very important that we're all of the same sign, because when you're crossing that center line position, you're adding angularity into your machine, and angularity is the worst thing you want to leave in the machine.
Great. Chris, Jill, I see you have your hand up. Is that for a question? Okay.
No, I just raised my hand when you asked me to the first time. Is it still? I'm sorry, I'll take it off.
No worries. And I see Mike removed his hand.
Yeah.
Oh, no, wait.
And
Yeah,
a lot of
let's
people, just mentioning this, a lot of people ask, why do we still use reverse dial alignment? A lot of your, especially the more advanced lasers, are based on the same system, but what it does on a plotting on a graph, it gives you that visual, and everybody can easily see that. and easily understand it. So it's like a precursor to using the laser, and you'll absolutely understand what's going on in the background of the laser systems.
Perfect. Just before we leave this section, does anyone have questions so far? Maybe you're shy. Yeah, okay, I've got one. Cassandra, please go ahead.
I had a comment. It was just about the dial indicators. We use those as well just to give the technicians a background before they start using the laser alignment. So yeah, we use the rough dial or the dial indicators reverse.
That's great. Yep. We love lasers. They're usually the fastest, most efficient, effective way to do an alignment, but we have to have that understanding before we go there. So I believe that's the absolute right thing to do.
Reverse dial is a good stepping stone to laser alignment. Thank you, Cassandra. And Julian.
Yes. So you're using a 1 thou tolerance per 1,000 RPM of rotation. That
Well, when you put it that way, pretty much we consider that precision tolerances or precision standard, anything 2,000 and below. And of course, there's a little leeway for really, really slow machines, but 2,000 RPM and below, we try to get it within 2, all on the same side of the line. 2,000 RPM and above, within 1. And you know, when you get some of that ultra precision equipment that's running 15, 20,000, you want to be on spot with that. So yes, but those are precision tolerances.
Perfect. Anyone else have questions? Next section. Oh, Benjamin. A technician was talking about, I don't think you see it, Dina. So he says,
it was something about a lift check. It went away, but it was something about a lift check.
Yeah, he said some of their technicians talk about lift check. How is that significant or relevant or compare with what we're talking about now?
Absolutely. Before putting a machine in or putting a machine together, you should do a lift check. And it's just out on the end of the shaft of your gearbox, your motor, your pump, whatever that piece of equipment is. Because too much movement can tell you something may be going on with that bearing and the clearances in that bearing, especially if you're reusing equipment. But it should also be checked on new equipment when you put it in, so you'll know what your baselines are, or if you know what kind of bearing it is, you could pretty much know what you feel. A lot of times, if you're just doing it by hand, you kind of have to know and be very, very familiar and know what you're feeling for. But you can also put a dial indicator there and know what the movement in that shaft should be versus what it is.
Okay. Somebody else is asking, what should they expect for angular alignment tolerances?
Angular foot?
Angular.
Angular, same thing. It still applies, because when we talk about that 2 thou or that 1 thou at every measured point across, keep in mind we want to be on the same side of the line. If you cross that center line position, that's angularity. And of course, angularity is much more stressful on our machine in most cases than parallel.
Okay, thank you for your question, Ebenezer.
We have to keep in mind that angularity is expressed over distance. So a little bit over here at the coupling is a lot out here at the end of that motor or that pump or whatever, 30, 40 inches out on a gearbox or something. That's huge. Yep. Thanks.
Okay. Let's keep going. Thermal growth, one of my favorites.
Yeah. Yeah, we have to take that into consideration. You heard me say a little while ago, we wanted that within tolerance at its normal operating state. Keep in mind that a lot of machines change when they heat up. So we may have to go out and do some calculations. These calculations need to be done well ahead of time, though. A lot of people like to do a hot alignment check or go by some parameters that was given to them from a vendor or something, and they don't know they're operating parameters and so forth. So we really need to go out and do some checks. Of course, you got to consider things like thermal soak if you're trying to do a hot alignment, where that machine soaks it in, but then that heat curve changes really, really quickly. So in today's environment, by the time you get it locked out, it's already changed. So how can you get a good accurate measurement? And we know that thermal growth is based on what? The coefficient of expansion of that material, the change in temperature of non-operating and the operating. So you're going to get, and usually it's a minimum of 4. If it's a bigger machine, you're going to get more in the plane of the foot, from the bottom plane of the foot to the center line of the shaft, because that's the area we can control. And you're going to get while it's normally operating, and you're going to get it when it's down, and sometimes it goes back to ambient, sometimes it doesn't. And we'll work all that out, and that will tell us how much that particular foot is going to grow. And there's software and there is charts and so forth that you can use for that as well, to just work it out. So it's not as complicated as it sounds, because it's just step by step if you follow those steps. And this is just showing you the minimum of 4, no matter how small that machine is. And you'll notice where the readings are taken, the little red dots in the plane of the feet. We get that average temperature, that change, and multiply it out by the coefficient of expansion and the height over which it's taken. Oh, we didn't talk about pipe strain, but we know the pipe strain affect our machines, and this is probably not a pipe strain problem. But here, if you look at this is a gearbox, and you want to make sure that the hot temperature you're actually getting, especially if you're going out getting readings for thermal growth or something, are the actual readings for that machine. And that's why I stress under normal conditions. If you take a look at this is a gearbox. If somebody had went out there who did not know that this thing wasn't supposed to run at like 260, if you look over to the side, they would have took those readings and went back and did some calculations, and they would have been way off. But that person noticed and questioned it, and they went and checked, and somebody had accidentally filled this thing with oil, or almost full, and it got really, really hot. And of course, if you look at the next picture, when they got the right level in there, this is what it cooled off to. It's pretty normal for a gearbox to run around 140 or a little more, right? But that would be the normal running temperature. But you can see how far off that could throw the calculations. So we have to be very, very aware. And like it says there, approach with an open mind.
Yeah. One of the things about thermal growth and pipe strain, I find when I go at various plant sites, it's one of the least executed calculations, and I would say it's quite rare that I go on site and I find that they know how to do it and they do it systematically. And I'm curious if my experience going on various sites actually matches what you, the people on the call, see this. So would you say that you are, if you or some of the people at your plant are quite proficient in this domain and you think you have it covered, could you raise your hand? Not a lot, eh? 1, okay. 2, 3. So as you can see, great for you guys that you have that expertise. But as you can see, that's a much lower percentage of the people on the call. I don't know. This is like 5 or 10%, not even, of the people on the call. So we tend to find that one of the domains where people have tackled a lot lately is, for example, misalignment. So a lot of plants work on that and adapt that. But when it comes to certain other pillars of precision maintenance, and I don't necessarily know why, but for instance, thermal growth, it tends to really get missed. That's the best word I can say. It tends just to not get done and be one of the leading hidden causes of issues. That's good. That's good that you have that, Julian. As I said, it is great that you guys have that, but it is really unique. So not a lot of plants actually have that level of diligence in their precision maintenance. And I think for a lot of the people here in this call, this would be probably a focus point, an interesting focus point. Julian, did you have something you wanted to say? Have your hand up.
I just haven't been able to lower my hand.
Oh, okay. Yeah, I'll lower it for you because I'm sure your hand's getting tired by now.
Balance and balance retention. Let's talk about it a little. And of course, we know that we want our machines to run true to the centerline position. When we have a heavy spot or something on something, whether it's a shaft, impeller, or a fan, or whatever, what it does, it throws that center off of the center of geometry. And of course, those vector forces spread forces across your entire machine. Unbalance is simply a mass times a radius. So we need to balance our equipment. And of course, there are different balance standards out there, and you have to decide what's right for your machine. Problem many times is most people, when they're ordering component parts and so forth, don't even specify. Don't even specify. And of course, what is the role of a technician around balance? Of course, is to retain the balance quality that's there. But like I said, we need to specify so we know what we're getting. And a lot of times we need to be able to check. And of course, when we talk about assembly errors, many times assembling component parts so that they do what? Improve the balance across that machine. You heard me mention keys. Matching the weight that was removed when those key seats were cut out. You heard me mention like set screws. Most people think anything about a set screw, but tighten it or torque it down anywhere. If you got set screw collars like on pillow block bearings, one on one side, one on the other, and you don't set those set screws up correctly, then you're going to put the center line in a different plane and you may wobble across that system right there. So we want to set them up in the same plane with each other. So we run true from one collar to the next, because you've created a whole different new center inside of that collar because you have, in most cases, sliding clearance there. So it does move in there if you don't set them up right. So what causes it? We talked about casting before, the mass distribution. Casting porosity is not always true, right? Machining errors. You know, how do we know that was bored on center? How do we know? So if someone in the squared up, true it up in the lathe when they bored it out, it may not be right. We need to be able to check those things. And like we mentioned, assembly of multiple component positioning, how we position things. You know, we talked about the keys. Most of the time, we want to turn those keys opposite each other to do what? Get rid of any residual unbalance of that rotation around couplings and so forth. And of course, the operation of equipment, like we mentioned, adhesion, erosion, corrosion, anything, repair, welding, your lubrication. Anything that changes the mass of that equipment can change the balance. And just a few balance specs there. Generally, most people try to go to a G1 on most equipment. There are some you can get away with a little more, G2.5 or G6.3. If you're not ordering at a specific spec, you're probably getting G6 or a little higher sometimes. So do keep that in mind. And of course, bearings, lubrication, and couplings. You know, everything we've talked about pretty much will help extend the life of our bearings. Bearings are tough, and most of the time the manufacturers say it should last somewhere between 11 and 22 years. I've seen bearings older than that. So we know we can get that life out of them, but many of the things we do, we cannot. So if you take a look at this failure categories, you have installation, lubrication, operating, and environment. All of those are contributing factors depending on how we handle things, from the shaft fit to the housing fit, how we handle the bearing ourselves. In the lubrication, did we do too much? Did we do too little? You know, did we go to it too often? Did we choose the right viscosity of that fluid? In the operating, usually when you think of operating, you think about the operations of the machine on the operator's side. But look at that, misalignment, unbalanced, belt tension. All those things cost us life in our bearings. And of course, the environment, things like contaminants, not having the right seals for that environment, vibration and so forth, electrical current passing through it and putting that pretty pattern in our bearings, that's going to kill it. And of course, phosphorinelling, like we mentioned earlier. You know, we should be rotating our spares out in the field that are not running at the time, rotating them in and out of service every week or every 2 weeks, depending on how much vibration is in that area. Or the spares that's sitting on the shelf, we should be rotating those. And I must say now that most people are doing that, but there's still some missing.
Yeah. I also want to add, so from the Spartacus side, we can see KPIs for various plants customers that use our platform. And one of the things that is, I would say, at least 9 out of 10 plants in their top 3 most common failing components, bearings are always there. And they're always there. I said 90%, but I think it's more than, quite frankly, I'd say it's more than 90% of the time they're in the top three, sometimes first and second position. So bearings are, as we all know, they're very prone to failure. And what makes it complicated or challenging to handle is that there's so many different ways so many different potential causes that can lead to the failure of the bearing, and they're very sensitive equipment that need to be treated with proper precision maintenance.
Absolutely. And of course, that's a bearing failure categories chart here. And you can see 36% back when this study was done, 36% was the lubrication causing the failure. And a lot of times that goes to contaminants and so forth, how clean our lubricant is and all. Because keep in mind, we have very minute clearances in most of our bearings, so it doesn't take much to destroy that. And of course, 34% installation and handling. So if we do that right and lube it right, there you go. You got 70% chance right there. And then of course, there's environmental and operational issues that contribute to failures as well. Symptoms of a failing bearing, temperature. Keep in mind that a hot bearing does not always mean that bearing has failed. It could be hot because somebody put too much lubricant in it. Of course, if it's a bad fit or something, it's going to eventually fail. And of course, it could be getting heat from external sources in some cases. Now, when you start hearing noise or the vibration level goes up on a bearing, usually that's really telling you something. And with some of those simple tools, like you see that little chart out to the side, you can use like a meter or a pen or something. Your technician in the field can use something like that to maybe make some determinations of what might be happening with that bearing.
So how many of you guys regularly use ultrasound during your lubrication to ensure that you've put in the proper amount of grease or in there? Okay. Few. Decent few. So personally, I've seen the transition in multiple plants. Those that did not use it, and then those that do use it. It's one of those things that I consider a quick win in terms of it's easy to learn. It's quick to learn. It's not the equipment is not particularly expensive within the usual prices for items in a plant, that is. So usually if you don't do ultrasound lubrication at your plant, I highly recommend to look into that. It really helps a lot. And you'll know if you didn't. You'll know a couple of things. You'll know if you've put the right amount of grease, but you also know if it's been too long since the last time that you greased your bearings. Yes, Benjamin. Critical. So okay, so I see you. So you're using, in your case, you're using them only for critical equipment. Choose proper baseline on the acoustic loop check. How do you recommend to use to create a proper baseline on the acoustic loop check? I have many different strategies that I use with my customers, but I think that maybe Dina, you might want to answer it. So, how do you define a proper baseline for when you do lubrication greasing?
In the beginning, making sure that you put in the right amount and check it. So many times you would have to do some calculations and so forth. And then it's usually like a re-loop and it gets like 8 decibels above. But initially you have to start there's some calculations you can do for that particular bearing, the type, speed, and style to know exactly what should go in there.
Yeah, absolutely. And I'll give you another that we do with a lot of the plants I work with is, if you don't know what the decibel level is, well, if you're using Spartacus, you can do that, but track your decibel level. Enter the value that you have. After you've done it for a couple of weeks or months, usually a couple of weeks, you will already know, first off, what is supposed to be your baseline, because this machine is supposed to be the same as the other ones, and that one's the lowest decibel reading you can have. If you know that, that's the lowest you can get to, and that's an attainable value. Anything above that, you're starting to either have a defect or you have improper lubrication going on.
Yeah.
Cassandra?
That's true.
Yes, I was gonna say we're trying to convert currently from doing time-based certain amount lubrication for our bearings to going to ultrasound. So we're sending our vibe tech to UAE training. But I was wondering, is it typically the vibe tech or the lube tech who takes the ultrasound training and the bearing work?
For the plants that I work with, it's the lube techs that they do it. They have the grease gun in one hand, they have their little the headset going on, and they in our case with our customers for the Spartacus side, they often mark down the value as found, so decibel level as found, and what they left it at after greasing. Okay, so that you can have two trends. You can see if you're able to return to that baseline all the time, or if you're starting to go up permanently. If you're going up permanently, you probably have a problem. And when you return, depending on the decibel level, it might give you an indication if you're coming too often, and it's kind of pointless, or if you're coming not often enough, because you're able to go back to your base level, but the increase is too substantial, and you would want to not get that high between the baseline and the measured reading when you arrive.
Okay.
Julian?
Yeah, we tried the ultrasound headphones and stuff like that, and we were kind of under the impression that so we went to a bearing that the vibe techs and stuff had flagged as maybe needing lubrication. It was getting noisy and all that kind of stuff, and we thought, okay, so it would be a perfect thing to try. We apply grease and we're gonna listen for a change in the level, and it's gonna be great. We couldn't hear anything different. So what you're saying is that you actually have to be measuring and noting decibels on it's almost treated as a vibration signature. And then you get a level, and then you look for, what are you saying, 8 decibels lower? So we weren't sold on it, because when we tried it, we tried different ones, and maybe the equipment we were using, but we couldn't hear a difference. Like, I don't know if it has to be like a measured value versus just your own hearing. But I was under the impression that it was going to be pretty obvious, and it wasn't for us. So I don't know if you have any comments on that.
It's pretty odd that you didn't hear any changes. Did you see changes with the decibel level?
No, no, because so we were there, we were adding degrees, and we're seeing there wasn't much of a change. So I was wondering whether the change is very, very subtle and you need some special analysis afterwards. But I was kind of under the impression that, it was going to be pretty obvious. It's going to be loud, and then it was going to quiet down. But that wasn't our experience. I tried it a couple of times, and so we haven't actually purchased it, because when we tried it, we didn't find it to be something we can just hand to the technicians. But maybe the type of equipment we were using, I don't know, maybe be open to trying it again. But
yeah, it is bizarre. Obviously, there can be what reason, there can be many. There can be, first off, you have to set it your ultrasound equipment to like tune it, call it that way. But beyond that, it is supposed to be quite evident. It sounds like a bit like a waterfall that calms down, basically, sort of waterfall sound that calms down once the lubrication is proper. I would invite you to re-explore that, maybe that equipment that you were using, or maybe, I don't know, there could be a couple of reasons. But at the various places where some of my customers use it, they go towards that and they don't go back.
okay,
All right.
sounds good. Thanks.
Great. We have a few more slides and not that many minutes, so I will let Dina take over.
Okay, when we're talking about lubricating, probably one of the most important characteristics, whether we're talking about oil or grease or whatever, is the viscosity. And this is just a simple chart showing you the effects of heat or temperature on viscosity. Of course, they're doing a comparison with like some 10W30, and you can see what it is when it's 30 degrees on a, well, it's 10W30, so we'll play like it's a vehicle, 30 degrees when you start your vehicle up, and you're out there about 400 or so kinematic viscosity centistokes, and then you get down the road a little ways, and you're at 100 degrees. It has changed already to around, what, 60 or so, if you look where it crosses that. And of course, normal running temperature around 190, 200 or so. You're down to, with a 10W30, you're down to what, 14, 15 or so. So that's huge, because that viscosity is what keeps separation. So I know I was talking about an automobile here, but when you think about your bearings and so forth, that keeps that separation, especially particularly when it goes through the load zone. That keeps that separation. So it's very important that we choose the right one. And of course, grease. You got the NOGI numbers for grease. It goes from like 000 all the way up to like a 5. I think there's a hybrid of a 6. So we're talking about something that's very fluid up to a block grease. But what I want to say here is most of your greases are at least 90% oil. What we're seeing is the thickener that pretty much holds that oil in place. Never confuse your thickness of the grease with the viscosity of the oil that's in it. You need to know what that viscosity of that oil is according to your system. And of course, we talk about relubrication, and of course, that's dependent upon a lot of conditions. Like Mikhail was saying, people have gotten very successful with the UE, but it depends on the grease that you're using. Many times the operating conditions and temperatures, some people lube because they're exposed to a lot of contaminants and so forth. Bearing size, bearing speeds, bearing style, it's a given. And of course, relubrication intervals. There are some simple formulas according to your bearing, and I think it's over on the next one, that can tell you how much should go into that bearing. But a lot of times it comes up to quite a bit, and you don't want to put it in there all at one time. So you have to decide, according to your conditions and so forth around that machine, how often you're going to go to it. So you would use a chart like this and use things like speed and the bore size of the bearing. And if you look at those 3 columns out to your left, there's an A column, B column, and a C column. And there are different types of bearing: radial ball bearings, cylindrical roller bearings, spherical bearings, carb bearings, and so forth. In this example with the 100 millimeter bore bearing running at about 1800 RPM, you'll see radial ball bearings need that amount of grease that you've calculated about every between 6 and 7,000 hours or so. The thing of it is, there's only 8,760 hours in a year. Would you wait that long to put that much in there? And you wouldn't put that much in there at one time, so you have to divvy it up. So you would divvy it up if that's a bearing you're going to go to every 2 weeks or once a month or whatever, you divvy that up. But what I really want you to notice is when you change your bearing styles, it really, really changes. That B is cylindrical roller bearings. It cuts it in about half. So you go to those much more often. That C column, talking about spherical bearings, wow, it's down to a little over what, 600-700 or so. Yep. So it depends on your bearing. And of course, this is just the relubrication quantity. You're calculating what that bearing needs. Make sure that you know your grease gun, especially if you're not using UE or have a meter or something. And it says grease gun calibration. You're not actually calibrating your gun, but you want to know what the output is, because there's different types of guns out there. And if you don't have a meter, you need to check that gun to see what each pump or whatever is worth. And of course, the conclusion of that is we have to know what greases are available to us, what kind of bearings we're using. And of course, speed is a consideration. How many times can we effectively lube that bearing in a year or whatever? How many shots per ounce to the grease gun we're using? Or if you're doing it in grams, calculate it that way. And of course, always question ourselves and see if our process is correct. A little bit on couplings. When we select a coupling, a lot of times we go with what we know, and that might not be the right coupling for that. Past success with a single manufacturer, or we already got those in store, so why get a different one or whatever. Ease of installation, everybody loves that, but it might not be the right thing to do. And of course, those sold as a cure-all, because Not beating up on the coupling manufacturers, but you will hear them say, well, my coupling can take 30,000 misalignment. Keep in mind that yes, their coupling can, but what are you going to be changing out? Bearings or motors or pumps or gearboxes, because it's going to what? Put those forces back right back down the line of that shaft, and everything else on that shaft is going to do what? Destroy itself from those forces and that misalignment, taking clearance out of bearings and so forth. But we'll be changing out those bearings or motors or whatever, but we'll put that coupling right back in there because the coupling's so great. That's not how we should be doing business. And of course, you should always ask whether you want it torsionally rigid or torsionally soft. And this is just a few examples. You know, you get torsionally soft with lube, torsionally soft, that is lube, without lube. And then, of course, you have your rigid style couplings the same way. You can get them lubed and no lubed as well. But you have to match the coupling to your machine set, not just what we like, or easy in and out, or sold as a cure-all, like we mentioned. Always make sure we use the proper coupling gaps as specified by the manufacturer. Check in, play, and so forth on your equipment to make sure that won't affect anything. If it's one of those big old motors that has plain journal bearings in it, make sure you find the magnetic center before you set it, because it will find its center and it'll jam you up and thrust against those bearings, or it'll try to pull back on you and it'll end up costing you life on your machine. Summation, we have only scraped the surface, and I'll let Mikhail speak.
Yeah, so that brings it to the end of the presentation. Thank you. I know we went a little over, and I'm taking some extra minutes of your promised 1 hour. There was a lot of content to look at. I just want to remind everybody here. So what we did today is give you an overview of precision maintenance. We didn't go into the process of each of them, how to correct them, how to assess them, how to train, you know, to assess if you're trained or not trained. So there's a lot of different pillars in precision maintenance, and those are also just the ones that we presented today. So if you're interested in this and you want to learn more, you think you might need coaching, maybe you want to have a process in place, maybe you want to have your technicians participate in some dedicated and certified courses. So we give all these things.